Hi everyone. In today's video, we're going to continue our discussion on alkanes, specifically now looking at cycloalkanes. We will focus our attention on a specific kind of cycloalkanes called cyclohexanes and go through the conformational analysis of these compounds. It is my goal that by the end of this video, you'll be able to rationalize the relative stability of cycloalkanes, draw the chair conformer of cyclohexanes, identify the axial and equatorial positions in cyclohexanes, draw ring-flipped conformers of cyclohexanes, and you'll be able to rationalize the difference in the stability of these ring-flipped conformers. So we're going to begin our discussion on the definition of a new kind of strain called angle strain. So the angle strain is a strain that is incurred by a molecule when a carbon that has 4 electron groups within that molecule deviates from that 109.5 degree angle. For example, if you take this molecule cyclopropane, you might guess, and I would actually encourage you right now to build up cyclopropane using your model kit. And what you're going to see is that there's a lot of angle strain in this molecule. Okay, so it's going to be incredibly severe because the angle between those carbons are going to be about 60 degrees, which is definitely below the 109.5 degree angle that you're expecting or you're hoping for a tetrahedral carbon. There's also significant torsional strain in cyclopropane. And remember that torsional strain arises from the eclipsing of bonds. For example, if we look down the Newman projection down that bond as indicated through that I, the Newman you're going to see is going to look like this, where two CH bonds or two pairs of CH bonds are going to eclipse each other. So what you will see are these eclipsing CH-CH bonds, which as we know is going to incur an energetic cost. And it turns out that because you have the cyclopropane, it's so strained, you actually can't deviate from this. So you're stuck with these eclipsing CH bonds. Cyclobutane, on the other hand, does indeed have less angle strain than cyclopropane. And in fact, when you build the molecular model kit for cyclobutane, you would see that you can actually bend that out of planarity. So it looks more like this, where we experience what we call a puckering effect or a pucker on that ring. So that ring actually kind of bends out of planarity. And in many ways, the reason why it does that is to avoid having a bunch of eclipsing CH-CH bonds in cyclobutane. Cyclopentane, on the other hand, has much less angle strain as well as much less torsional strain in its molecule. Cyclopentane looks a little bit more like this, where certainly most, if not all, of those CH bonds are no more eclipsing with each other. So there's a lot of bending and puckering in cyclopentane in order to avoid torsional strain. And then in our very special case, cyclohexane is a fairly unique cycloalkane because it actually has nearly no strain in this molecule. So the angles seem to be about 109.5 degrees, and there's really no torsional strain in cyclohexane. And so for the rest of this video, what we're really going to work on is just looking at the conformations of cyclohexane and how that exhibits itself. So let's talk about the conformation of cyclohexane. There's really one major conformation of cyclohexane, and we're going to start by focusing on that particular conformation. And this is the chair conformation. The chair conformation looks like this. So the way you can really see this once again is by building your model kit. So what I want you to do is build your model kit of cyclohexane, and I would like you to try to get it to look like the picture that we're showing you on the left hand side of this video. And And notice that in that conformation of cyclohexane, you can actually take the what let's call the leg rest. If you think about this as a chair, the leg of that cyclohexane could become the head of the cyclohexane, and then you can flip once again the head of the cyclohexane down to the leg. So you can do what we call a ring flip of your cyclohexane conformer. But before we go into that level of detail, what we're going to do is practice how to draw the chair conformation of cyclohexanes. So when I say practice, I really do mean practice. You really have to draw this cyclohexane chair as many times as possible until you get a complete hang of it. So step 1, draw a wide V. So then your step 2 is pick a head, so any of the edges of this V, and draw a 60-degree line towards the middle of the V. So I've done it this way in my own drawing. So I've picked the left head. Step 3, draw a line parallel to the other side of the V. And that parallel line should stop just before you get to the end of the V. So notice what I've done there. Step 4, draw a line parallel to the one you have drawn in step 2. So in this case, we're going to draw a line parallel to the purple line. And what you also want to make sure is that that line reaches to the bottom of that chair conformer, so it looks like you're stopping on the same location height-wise. And then finally, step 5, connect the line you drew for step 3 with the line you drew for step 4. And that is your cyclohexane chair conformer. So this is one chair conformer of your cyclohexane. So remember, you could have your step 2, you could have started from either the left end of your V or the right end of your V. So in this first scenario, I started with my step 2 purple line on the left end of the V. So I'm going to redraw this molecule and start from the right end of the V on step 2. Okay, so there you go. That is the other potential way you could have drawn that chair conformer. So I'm hoping that you're able to trace this as well. And like I said, this is the time to just stop and draw this chair conformer at least 50 times before you move on in this video. And it's your goal to get to the point where you don't even need to look at these steps anymore. You can just draw it at at a very quick pace. Okay, so let's look at the cyclohexane ring flip again, just so we can really think about this a little bit more deeply. So I'm just going to denote one location on a cyclohexane, and we're going to try to do a ring flip. So a ring flip is, like I said before, you take the head of your chair, so that's where I have the X at this point, and you twist that, and then you take the tail or the leg end of your chair and then you twist that up. So you're twisting the head down and you twist the tail up. And if you're following, what you're going to see is that X would essentially get down to become the tail end or the leg end of your chair. And it would kind of flip a little bit to the point where it's no more kind of going up and down on the ring. It's going a little bit to the left and to the right of that ring. So we're going to go into the detail a little bit later, but what I want to do is just show you that, in fact, when you do a ring flip, the cyclohexane actually goes through a series of conformers in order to get all the way down to the other ring flipped conformer. So if we sketch out a potential energy curve where we start on the y-axis with potential energy in kilojoules per mole, and on our x-axis just the ring flip motion. So we start with the chair conformer, like the one we've seen on the left-hand side of the equilibrium arrow. That chair conformer is going to go through what we call a half chair. So take that tail or the leg end of your chair and then twist it upwards. You're going to go through what we call a half chair, where it kind of looks like a lawn chair in some ways. And then there's a conformer that you're going to actually go through, and this is a little bit harder to see when you're twisting your molecular model kit, but it goes through what we call a twist boat. So it almost looks like a boat that one side of the boat has been twisted upwards. We then arrive at another conformer called the boat conformer. So this one is probably a little bit easier for you to get to from your molecular model kit. But yes, so then you have your what you call a boat, where essentially you now have two heads and there's no more leg of your chair. So both the leg part is completely twisted upwards. And then the rest is basically the mirror image. You take the other side of your molecule and you start to twist it downwards, where you return back to another twist boat, just now the opposite direction. And then you get to the half chair. So now the mirror image of the half chair you drew earlier on. And then finally to the ring flipped chair. So what we drew, that equilibrium going from one chair conformer to the other chair conformer, is actually a series of conformers in between, right? You go from a chair to a half chair to a twist boat, then to a boat, back to a twist boat, back to another half chair, and then all the way to the next chair conformer. We do have some energies to back this up. So it turns out to get from the chair to the half chair is about 45 kilojoules per mole. And then the energy difference between a chair and a twist boat is 25 kilojoules per mole. And then the energy difference between a chair and a boat is 30 kilojoules per mole. Okay? So keep that in mind, that the chairs are ground state conformers. And in fact, those half chair and the boats, those are transition conformers in between the chair and the twist boats. Okay? So just keep that in mind as you're kind of looking at these cyclohexanes. When you're kind of flipping back and forth, you're actually really going through a series of different conformers. Okay, so now we're going to delve a little bit deeper into looking at the chair conformer and actually analyzing the substituents positions on the chair conformer. Okay, so here is a chair conformer of a cyclohexane ring. And what I want to do now, and this is what something you also absolutely need to practice, is the relative spatial location of all the substituents on a chair conformer. So the way to think about this, the easiest way to think about this is realize that there are three positions on the chair that you can consider your kind of your up positions, if you will. And I have starred those. So these are the places where the bond lines are pointing upwards or in the upwards trend. In these positions, there is going to be a substituent that will be pointed directly vertical and upwards on these positions. And I have drawn those vertical and upward substituents on these positions. Now, then you look for the other three positions. So these are the ones that are where the bond lines are pointing downwards. I've once again marked an X on all of these three positions. Here, there's going to be a substituent that is also vertical, but pointing downwards. And I have drawn those three lines pointing downwards, okay? All right, so these six positions that you have just drawn and these six spatial locations, notice they're always going up or down depending on the location on the cyclohexane ring. If you have a substituent on those positions in those spatial locations going up or down on the ring, we call those axial substituents, okay? And now we're going to look at the other potential spatial orientation. So now what you want to do is split this cyclohexane ring into two. So I kind of had a red dotted line in the middle of the cyclohexane. And so we're going to divide into two hemispheres, the left hemisphere and the right hemisphere. So now I'm going to try to fill in the rest of the substituents on the left hemisphere. Because it's on the left side of these dotted lines, all other lines are going to be facing the left side of the ring as well. So for example, I have drawn one on the head of this chair. So notice two things. One, it's pointing towards the left-hand side of the ring. Two, it's pointing downwards. And the reason why it's pointing downwards is that if you notice, you're actually drawing a tetrahedral carbon shape in that particular location. Okay, so that is that particular red line, let's draw the two other lines on the two other positions on the left hemisphere of your cyclohexane. Here you go. So once again, notice two things. One, both of those lines are also pointing towards the left. However, they're tilted upwards. So now you have these red lines tilted slightly upwards. Once again, it's to try to form a shape that looks tetrahedral. So those down carbons have these red lines that are to the left, but now pointing upwards a little bit. Okay, so that's the left hemisphere. Now let's draw the lines on the right hemisphere. And yes, you guessed it. They will be pointing towards the right of the cyclohexane ring, and you would try to form a tetrahedral shape. So at the leg rest of your cyclohexane chair, that red line is pointing towards the right and somewhat upwards. And then where your knees on the cyclohexane chain would be, the red lines are still pointing towards the right, but somewhat downwards as well. A substituent on any of the red lines are considered equatorial substituents. So we consider these equatorial because they're sort of like, they're the equator of your cyclohexane chair, right? So they're kind of around the cyclohexane chair, as opposed to the axial substituents, which are pretty much above or below the cyclohexane chair. Okay, so let's draw this molecule called fluorocyclohexane. Fluorocyclohexane is just a cyclohexane with a fluorine on it. So what I'm going to do now is draw one chair conformer of fluorocyclohexane. So here's a cyclohexane chair. But now you can really, in many ways, you can put the fluorine at any location on the cyclohexane chair. But you have to make sure that the orientation has to be either axial or equatorial on the cyclohexane chair. So in this case, I'm going to make it axial, and I'm going to put it on the head of the cyclohexane chair. Okay, so at this point, I want you to build up this molecule in your model kit. And then I want you to convince yourself that this particular conformation of a cyclohexane chair is identical to this conformation, and that conformation. So all of these I have drawn are identical in conformation to the one I drew on the left-hand side. And the way you can figure this out without having to rotate your cyclohexane chair model kit is by seeing that in every single one of these cases, that fluorine has remained in the axial position no matter how you've drawn it. They've all been axial. So because that fluorine has remained axial going from the left structure all the way to all three of these, they are basically the same conformation. The only difference is the way you are looking at that cyclohexane ring. That's what is different, is your perception, not the actual conformation of this particular molecule. However, the molecule I have now drawn at the end of those equilibrium arrows is now a different conformer of your fluorocyclohexane. And the reason why you would know this is that fluorine has gone from being in an axial position and has moved into an equatorial position. So if you do any type of cyclohexane ring flip, your axial substituents will always go equatorial and vice versa. Once again, convince yourself that the three other molecules I've just drawn to the right of the equatorial fluorocyclohexane is exactly the same conformer. And that's because that fluorine has stayed equatorial in every single one of these structures that you've drawn. Okay? So the moral of the story is, whenever you do a cyclohexane ring flip, all substituents in the axial position will always move to the equatorial position, and all substituents in the equatorial position will move to the axial position. So that's the definition of a cyclohexane ring flip. If you see two orientations in which the conformers stay in their axial or equatorial position, you have not done a ring flip. You've just changed your perception of how you're looking at that same molecule. Okay? So that would just be identical molecules oriented in different ways. Okay. Lastly, let's talk about the stability of the chair conformers of cyclohexane. So consider Methylcyclohexane in two conformations. So one, this is your equatorial position. And here's a ring flipped conformer where the methyl is now in the axial position. It turns out that at equilibrium, 95% of methylcyclohexane will be in its equatorial position, whilst 5% will put the methyl in an axial position. And just to clarify, ME, we would typically put ME to stand for methyl, which stands for a CH3 group at that position. So just think about ME as CH3. So why is it that the majority of methylcyclohexane will exist where that methyl is in the equatorial position? The answer is a phenomenon we call 1,3 diaxial interactions. So a clever way to think about 1,3 diaxial interactions is to remind ourselves of another interaction that we absolutely do know about. So imagine you had butane in this particular conformation, and you wanted to determine the Newman projection as looking from the position of that eyeball. This is sort of your butane in this particular conformation. And recall that in this conformation, your butane is going to experience what we call gauche interactions that are affected when you have two CH3 groups 60 degrees from each other. Okay, so like in this case, let's assume that we're looking down the Newman from both of these bonds on a cyclohexane. And then we're going to call the carbon on the right carbon 1, and we'll call the carbon on the left carbon 3. It's my hope that you will see that the Newman for carbon 1 should look something like this, very similar to what we had for our butane Newman. But then if we were going to continue the Newman projection where you have to include the Newman on the for carbon number 3, it's my hope that you will see that carbon number 3 Newman should also look like this. Okay, so you should expect two Newman projections that are sort of essentially just connected by two CH2 groups. So notice that in this particular conformation, you have this CH3 group that is very close to a CH2 group in an interaction that looks very similar to a gauche interaction. So we call this a 1,3 diaxial interaction. But the key thing to realize that a 1,3 diaxial interaction is simply a gauche interaction, however, happening in a ring. So that's really what it is. It's just a gauche interaction in a ring. So let's look at what that looks like spatially on a ring. Okay, so what I have done here is I've redrawn the axial methylcyclohexane. Now I'm going to explicitly show you that CH3 or the methyl group in its full glory. And I've also shown you the axial hydrogens that are 3 away from that methyl. So think about this as 1, 2, 3. So the carbon 1 is the carbon bearing the methyl, and the carbon 3s are the carbon bearing those axial hydrogens. So in pictorial form, it's that steric clash between the methyl group and those hydrogens that are considered 1,3 diaxial interactions. So whenever you have a group that is on the axial position, it can run into that interference essentially with the other axial hydrogens 3 carbons away from that particular R group. Okay? So the take home here is that 1,3 diaxial interactions is the unfavorable steric interaction that arises when substituents are placed in the axial position of a ring. Because once you put these substituents in the axial position of a ring, it can run into that risk of engaging in unfavorable steric interactions with the hydrogens on the 3 position. And so it would make sense that the larger that group is, so the larger the group, let's say you go from a methyl to a third butyl, that 1,3 diaxial interaction will be even more and more severe. Okay, so that's really it. That's really it about the stability of chair conformers in general. Not always, but in general, the substituents would prefer to be in the equatorial position in order to completely eradicate these 1,3 diaxial interactions. Okay, so in this video, we've learned how to rationalize the relative stability of cycloalkanes, so from cyclopropane all the way to cyclohexane. We've drawn the chair conformer of cyclohexanes. We've identified axial versus equatorial positions on cyclohexanes. We've drawn ring-flipped conformers of cyclohexanes, and we've actually been able to use some old interactions that we've learned to rationalize the difference in stability between ring-flipped conformers of cyclohexanes. Thank you so much for watching this video, and I will see you in class.